Hello viewers, you're welcome back to my channel. This is the third part of the video lessons on measurement, and in the course of this video lesson I will explain in detail the following concept. And the first is the degree of accuracy, where we further explain the difference between reading accuracy and measuring accuracy. And secondly, we'll look at parallax error, or error due to parallax as it is popularly called. And lastly, we'll look at estimated uncertainty. So by way of beginning this video, I'm going to provide you with a definition of accuracy. And what is accuracy? Accuracy is simply the degree to which a measured value, emphasis on the word degree, and then measured value is close to the true or the accepted value. Now what does that mean? It simply means how close that value you have obtained by measurement is close to what is actually true. So it's very simple. Let's say we have a rod, a metallic rod here, and the true length of this metallic rod is 50 centimeters. And if I tell two students to measure this rod, let's say student A and then student B. So we have two students, student A and then student B. And student A measures the length of this rod to be 49.9 centimeters. And then student B measures this rod to be 47.5 centimeters. Now looking at their measurement, the measurement for student A, 49.9, is closer to 50 centimeters. So I can therefore say that this measurement is accurate. But looking at the measurement obtained by student B, it is 47.5, which is far from 50 centimeters. So this measurement is not accurate. So what we are trying to say in essence is that how close is that measured value from the true value. So if it is very close, we can say that measurement is accurate, but if it is far, we can say that measurement is not accurate. It's just like running a race from point A to point B, and the actual time spent for this race is 1 hour from point A to point B. And let's say two persons, A told us that the time spent for this race is 59 minutes, and then B tells us it is 30 minutes. 59 is closer to 1 hour than 30 minutes. So A is accurate and B is not accurate. So again, accuracy is simply the degree or how close the measured value is to the true or accepted value. And also, as I said in my previous video, I said that in reality or in life, when we are told to measure, there will be some little differences. So we are trying to ensure that that difference is not much, so that whatever you are trying to measure is actually close to the true or to the accepted value. Because when you tell more than two persons to measure a particular stuff, they will obtain different values. A can say that his or her value is 49.9, B can say it's 49.8, C can say it's 50, then D can say it's 30. So we are trying to look at how close that value is to the true or to the accepted value. In this section of this video, I'm going to explain the difference between accuracy and precision. Now, most persons think that accuracy is a synonym for precision, or they have the same meaning. But in real sense, accuracy has a different meaning from precision. So what is accuracy? As I defined earlier, accuracy is the closeness of the measured value to the true value. So let's say we have a piece of rod, a metal rod, and the length of that piece of rod is 50 centimeters, and a student obtains 49.9 centimeters. That value is accurate because the measured value, which is 49.9 centimeters, is close to the true value, which is 50 centimeters. So in that case, the student has an accurate value. But if another student obtains a value of 47.5 centimeters, that value is not accurate because 47.5 centimeters is far from 50 centimeters. So in real sense, accuracy is just how close the value that was gotten from measurement is close to the true value or the accepted value. So let's move on to precision. What is precision? Precision is simply the closeness of repeated measurements to each other regardless of accuracy. So in precision, we are trying to look at how the values we have measured, how close they are to one another. So let's take a good example. Let's say we have a piece of rod and the length of that piece of rod is 50 centimeters, but a student measures that rod for the very first time and a student got 43 centimeters. Again, the student got 43.2 centimeters. Again, the student got 43.3 centimeters. Looking at this value, 43, 43.1, and 43.3, they are far from 50. Hence, these values are not accurate, but they are precise. Why are they precise? They are precise because they are close to one another. 43 is close to 43.2, which is close to 43.3. So in this case, these values are precise because they are close to one another, but they are not accurate. So let me further explain accuracy and precision. There is this game called a dart, which makes use of a dartboard, as you can see on your screen, and a little spear or arrow, which is called the dart. So you throw the dart towards the dartboard. So when playing that game, your target is to get to this center portion. So the center portion is the target. So let's say we have 5 darts and I threw the 5 darts. So the first go to this portion, second go to this portion, third, fourth, and fifth. So in this case, I did not hit my target. So in this case, my throw was not accurate, but the throws, they are close to one another. So in this case, it is precise. So what we have here is that the throws are close together, which makes them precise regardless of accuracy, but they are not accurate because they did not get to the center portion. So let's take a second case. I threw my 5 darts and the 5 darts all fell in this center portion. Number 1, it got my target, which means that my throw is accurate. So my throw is accurate because it fell on the center portion of my target, and it's also precise because they are all packed together. So it is accurate and precise. So now let's look at the third case. Let's say I threw my 5 darts and then 3 got to this portion, 1 fell on this portion, 1 fell on this portion. So in this case, I have most of them at the center part, which makes it accurate. So this is accurate, but they are not all together at a particular portion. 3 at the center, 1 in this second portion, and 1 in the third portion. So this case is accurate, but not precise. Now bringing it down to physics, let's say we have a metallic rod. The true length of this rod is 50 centimeters. So let's say we have a first case. Somebody measures and got 49.9, another person 49.8, another person 49.9. Looking at this one, they are all close to 50 and they are all close within themselves. So this is both accurate and this also precise. So in the second case, we have 47.5, 47.4, and 47.5. They are all close to one another and they are far from 50. So this is not accurate, but it is precise because they are close to one another. Then if you look at case 3, we have 49.9, we have 47.5, and we have 47.8. Among the 3 of them, 1 is closer to 50, which makes it accurate, but they are all far from each other. 49.9 is far from 47.5. So in this case, this is accurate because one of the values is close to 50, but it is not precise. So I hope you understand the difference between accuracy and precision. In this section, I'm going to explain the difference between reading accuracy and measuring accuracy, and they are both types of degree of accuracy. So we'll begin this section by looking at reading accuracy. So as the name implies, it is the accuracy when reading values from a measuring instrument, either a stopwatch or a meter rule or even a thermometer. So in essence, reading accuracy refers to how precise a person can read the value of a measuring instrument. So I'll bring it down to this level. It is simply that smallest value you can read, how small or that tiny value you can get from a measuring instrument. So let me explain. So let's say we have a physics textbook and I'm told to measure the length of this physics textbook, that's from here to this portion. Now this point aligns with our meter rule. Now looking at this point, if I should trace this point to my meter rule, it falls between 2 and 3. Now in this case, there are no smaller units. So in this case, I'm going to try to be accurate and precise. So what am I going to do? Between 2 and 3 is like halfway. So half between 2 and 3, or we can go in this nature. This ruler is divided into one smaller unit, in the sense that from 0 to 1 is 1 unit, from 1 to 2 is 1 unit, from 2 to 3 is 1 unit. So in essence, this meter is divided into one division. But to get that accuracy when reading, especially when it does not fall on 2 on 3, I'm simply going to divide by 2. And 1 divided by 2 is 0.5. So in reading, this point is going to be 2.5 centimeter. So that smallest portion you can get when reading a measuring instrument is what we call the reading accuracy. So if the book extends from 0 to 2, this is obvious as 2 centimeter. But when it falls between 2 divisions or 2 graduation, we are then going to rely on what we call our reading accuracy. So in this case, reading accuracy is going to be 0.5, but in reality, it is written as plus or minus 0.5. What does that mean? It can be 2 plus 0.5, that will give us 2.5, or the next one is 3, can be 3 minus 0.5, which also give us 2.5. So in reality, it is written as a plus or minus 0.5 for a meter rule. Now let's take this other instrument, which is from 0 to 1, and in between we have 10 smaller division. First of all, since there are 10 smaller division, each of them is going to be 1 divided by 10, which is 0.1. So this is 0, this is 0.1, this is 0.2, 0.3, 0.4, so on and so forth. So in essence, every point is 0.1. But now let's say we have an object and the object falls between 0 and 0.1. How can we get the reading? So in this case, I'm going to say I'm going to take the division, which is 0.1, divided by 2, which is going to give us 0.05. So in this case, this point is going to be 0.05. So the reading accuracy is a plus or minus 0.05. So I cannot have it more than 0.05 and I cannot have it lower than 0.05. So in essence, to get your reading accuracy, find the smallest division, which is 0.1, then divide it by 2. If I have a thermometer, let's say I have a thermometer, and thermometer is, let's say, 27, 28, 29. So if you look at it, it is just calibrated or divided into 1 division. So from 27 to 28 is 1. So to get the reading accuracy is going to be 1 division over 2, which is 0.5, let's say, degrees Celsius. So in essence, find the number of divisions or the particular division divided by 2 to get your reading accuracy. So the next aspect is measuring accuracy. So measuring accuracy is just our definition for accuracy. Is simply how close the measured value is to the true or accepted value. So again, let's say we have the length of a football field to be 100 meter, and a student A got or measured that field and obtained a length of 99.8 meter, and a different student B got a length of 70 meter. A is accurate in the sense that this measured value is close to this true accepted value, but B is not accurate because this value is far from the true accepted value. So it's just our definition for accuracy. So we'll move on to the next aspect. In the last section of this video, I'm going to explain parallax error and estimated uncertainty. So we'll begin by looking at parallax error, and it is popularly called error due to parallax by students during physics practical examination. So what is this error? This error happens when there's an apparent shift in the reading of a measuring instrument when it is viewed from a different angle rather than being viewed vertically downward. So what does this tell us? Now when you want to read a measuring instrument, so let's say we have a measuring instrument MI for measuring instrument, we are supposed to look at this instrument vertically downwards, or we can say perpendicularly. So you see that you are looking at it vertically downwards, or you are looking at it perpendicularly. That means at an angle of 90 degrees to the measuring instrument. So you have your eyesight up above the instrument, then you have a measuring instrument. So you have to look at it straight vertically downwards, not from a side or not from this side. That means not from an angle. So what does it mean? We have our measuring instrument here, this meter rule. We have a meter rule. So when you want to read your values, this is the right way of reading a value. So you have to look at it vertically downwards. So in this case, by looking at it, I'm going to obtain a value of 2 centimeters. But when I view this instrument from an angle, let's say from the left, I can view it like this. We end up reading, let's say something like this. This could be 2.4 centimeters. So in this case, I'm getting 2.4 centimeters. So this is a wrong way of viewing a measuring instrument, or I'm looking at the instrument from the right hand side at a different angle. So I could end up reading something at this point, and this is 1.9 centimeters. So this is one of the things that can bring about error in measurement, and we should try to avoid it when reading measuring instrument. And how can you avoid it? You can avoid it by looking at the measuring instrument vertically downwards or perpendicularly. So lastly, we are going to look at estimated uncertainty. Now this concept is also called the maximum or the greatest possible error. Now when you are doing some measurement, they will give you like this. You could be given as 5 centimeters plus or minus 0.5. So this plus or minus 0.5 is what we refer to as estimated uncertainty. It simply means that 5 plus 0.5 is 5.5. Then 5 minus 0.5 is 4.5. It means that your reading should be between 4.5 and 5.5 centimeters. So if, for example, now an examiner gives you an exam, and in that exam, they know that the true value is 5 centimeters, and you are giving that exam to measure a particular thing. It could be length, mass, time, current, or whatsoever. They expect that every student answer should fall between 4.5 centimeters, for example, and 5.5 centimeters. So if you start getting 6.0, it means that student is totally wrong. So this is what estimated, what is the maximum value you can get. So they don't expect to get above 5.5, and they don't expect to get below 4.5. So this is a range of values. So anything beyond 0.5 is wrong. So that will bring about an estimated uncertainty or a possible error. So now what is estimated uncertainty? It's simply the half of the smallest deviation of a measuring instrument. So there's a formula for calculating estimated uncertainty or maximum possible error. So maximum possible error is simply half times the smallest scale deviation. So what does this mean? So let's put it to application. So this is a meter rule. The smallest deviation, this meter has been divided into 0. You have 1, you have 0 here, 1, 2, 3, 4. From 0, the next value you can see is 1. So that's the smallest possible deviation. So division here is 1 millimeter. So when we talk about the maximum possible error, let's say MPE for maximum possible error, it's going to be 1 times, or half rather, times 1, and this will give you 0.5. So in this case, the maximum possible error for this meter is plus or minus 0.5. So what does that mean? If you remember, when I explained the reading accuracy. I told you that reading accuracy is just that possible value you can get when reading your. So in this case, let's say we have an object here. We'll best call this 0.5. You understand now? So it's either I read from here 0.5, this 1. If I have something, this is going to be 1.5. So I can't have something as 1.58. That's not possible. Or the attempt to read something, I say that from this meter rule I got 1.5982. This is totally impossible because you can't get 982.5982 from this meter rule. So this is what will now bring about an error. So that maximum value you can get is what is 0.5 in this case. So in exam it is written as a plus or minus 0.5. So I can have 3 plus or minus 0.5. So for this other case, the smallest division is this. So from here, this is 0, this is 1. So in between there are 10 smaller divisions. So each of these division is 0.1. So this next will be 0.2. But let's stop here. So the smallest you can get is 0.1 in centimeter. So now the maximum possible error for this meter rule is going to be half times 0.1, and this will give us 0.05 centimeter. So the maximum possible error for this instrument is a plus or minus 0.05. In this question segment, I will answer 4 questions based on the topic that has been treated in this video. And the first question is, the maximum possible error in using a scale graduated in millimeters is. Recall from the past section of this video, a scale in millimeter has just one small division. What does that mean? If this is a meter rule in millimeter, the first, which is usually 0, the next is always 1. So it is read as 1, 2, 3, 4. So it is divided into one small division. That means the smallest thing you can read is just 1 millimeter. After 1 plus 1 becomes 2. Then the next is 3. So recall that to calculate the maximum possible error, it is half times the smallest division on the scale. The smallest division. So in this case, the maximum possible error is equal to half times the smallest division, which is 1 millimeter. So when you do the calculation, this is going to give you 0.5 mm. So answer to this question is B, which is 0.5 mm. So it's simply half times the smallest division. The smallest is what you can measure after 0. After 0, the next measurement you can get is 1. So our second question reads, what is the percentage error in measuring a distance of 5 centimeter using a meter rule that is marked in millimeter? So the meter rule is marked in millimeter, but I'm trying to read something of 5 centimeter. So the first thing I'll do, I'll convert 5 centimeter to millimeter. Now in conversion, 10 millimeter is equal to 1 centimeter. But what we have here is 5 centimeter. So 5 centimeter is equal to what in millimeter? So we'll take that as x and then we'll cross multiply. 1 times x is x. Then 10 here times 5 will give us 50 millimeter. So the next thing we are going to ask ourselves, what is the possible error in using a scale in millimeter? And from our question 1, the maximum possible error in using a scale in millimeter, maximum of a scale rather in millimeter is 0.5 mm. So this is the possible error. Now how do we calculate percentage error? From mathematics, percentage error is simply error over the actual value times 100. So in this case, our percentage error is going to be the error, which is 0.5 over the actual value in millimeter is 50 mm. So this is 0.5 mm times 100. So when we divide, this is going to be 1%. So the possible error from this calculation is 1%. So the third question is, a boy measures the length of a book as 48 centimeters instead of 50 centimeters. The question says, calculate the percentage error in measurement. Again, percentage error is equal to the error over the actual value times, since it's percentage, times 100. So in this case, the boy measures the length to be 48 centimeters. So this is the measured value. And instead of 50 centimeters, so 50 centimeters is the true or the actual value. So the error is simple, so we can calculate now. So the percentage error is going to be the error is simply going to be 50 centimeters minus 48 centimeters over the actual value, which is 50, because the true length of the book is 50, times 100. So 50 minus 48 is equal to 2 over 50 times 100. Now what does this tells us? It tells us that the error in measurement is 2. So in real sense, it can be a plus or minus 2. So now from here we have 2 over 50 times 100, and when we calculate, this should give us 4%. So the percentage error is 4%. So moving on, our fourth question reads, the diameter of a cylinder is 100 plus or minus 1 in bracket millimeter. Calculate the percentage error. So what we have here is 100 plus or minus 1. So in exam, when you see expressions like this plus or minus 1 is the error, then this 100 is the true or the actual value. So in this case, we can calculate the percentage error. Recall, percentage error is simply the error over the actual value times 100. So in this case, the percentage error is equal to our error, which is 1. We don't take the plus or minus, we use what to call the absolute value. That means that we are not bothered about the plus or minus. So it's going to be 1 over the true value, which is 100, times 100. So from calculation, 1 over 100 times 100 is equal to 1%. So the percentage error in this case is 1%. So if you enjoyed this video lesson and you learned something from this video lesson, don't forget to like this video, and also do it to share this video to your friends. And if you have any question or suggestion, do it to leave them in the comment section of this video. And to those who are new to this channel, if you haven't subscribed to this channel, do it to click on the subscribe button just beneath this video lesson, and also turn on the notification icon so that you always get notified whenever I release a new video. So till you get to see my next video, do have a wonderful time.